Hello everyone who participated in ISLPED 2020. Our research group will be presenting STINT, Selective Transmission for Low Energy Physiological Monitoring in the following 20 minutes. My name is Tao-Yi and I'm a computer science PhD student at UC Irvine. This is a work in collaboration with my lab mate, Kun Wonki, Professor Kain from Biomedical Engineering, and Professor Dutt from Computer Science. Before I show the agenda for this presentation, let me explain why energy-efficient physiological monitoring is important. At the time of recording, CDC statistics show that almost 2.5 million positive specimens of COVID-19 have been reported within the United States since March 1, 2020. These specimens are mostly nasopharyngeal swabs examined by molecular diagnostics such as RT-PCR. Although RT-PCR is proven to be the most accurate diagnostic tool for COVID-19, the examination itself is not only expensive but also poses risks to medical personnel who are involved in the process. Jian et al. Suggests that wearable devices monitoring the human body continuously and non-invasively may be a better alternative tool to help us either understand diseases such as COVID-19 or answer some difficult medical questions about chronic diseases. To leverage the power of state-of-the-art machine learning, we first of all need to build a sensor that is super energy efficient so we can collect as much data as possible. Nowadays, most wearable healthcare devices can generate multiple biosignals from the different sensors integrated in itself. However, none of the current commercial devices can withstand continuous operation without draining its battery within a day or two. The ultimate goal to set up a sensor platform that supports long-term, uninterrupted, and multi-biosignal monitoring imposes great challenges in low-power electronics design. Several pilot studies have shown that the more diverse the signals are, the better the prediction can be. It is also intuitive to see that longer episodes of continuous recording is more likely to uncover the elusive trends of diseases that change slowly over time. Since we are looking into the energy efficiency aspect of wearable sensors, let's take an example and analyze the breakdown of energy consumption of an asthmatic quiz quantification IoT device. From the bottom to the top of this chart, the sensor is enabled with different types of optimizations. These optimizations include different sampling rates, whether compressive sensing is enabled, and whether a classifier is available on the sensor or not. If we compare the baseline case, which is Nyquist rate streaming at 8 kHz, and the topmost configuration in which a classification algorithm is available on the sensor, it is evident that the processing energy trades off with communication energy. In addition, communication is much more expensive than processing. In other words, we can potentially exploit the abundance of computation power in newer microcontrollers to minimize the energy consumption in data communication. We have now covered the background and motivations behind this research project. Now get ready for the problem formulation and the STINT or Selective Transmission framework. Experimental results will follow the introduction of the STINT framework. Finally, we will reveal the takeaway message. To set up the problem, first define the baseline native system, which comprises a conditional transmitter that transmits each and every raw data acquired by the sensor. To make it energy efficient, we propose the STINT framework that modifies the transmitter to only transmit non-zero samples. In addition to the transmitter replacement, we added a selector to generate a mask for the raw samples. The objective of such mask is to zero out or effectively drop uninformative samples that do not benefit downstream data analytics tasks. In a nutshell, the problem can be formulated as a search problem of a selector function such that the number of samples chosen to be transmitted is minimized, and the samples transmitted are the most helpful for a specific task such as COVID-19 detection or arrhythmia detection. The selector function is chosen to be a multi-layer perceptron in the STINT framework. We choose MLP because it is less computationally demanding for the target microcontroller and has small memory footprint. However, this does not preclude any other type of machine learning model to be incorporated in our framework. We also need to define a task classifier C without loss of generality. We assume that C is a binary classifier that detects arrhythmic events from blood pressure waveforms. Training can be done by gradient descent guided by the loss function, which is the L2 distance between the probability estimate with complete signal and its counterpart partially transmitted signal. So as an optional step, we introduced confidence penalty to the loss function to encourage generalization of the model. The loss function effectively encourages selector to skip samples that have less effect on classification accuracy. Now let's discuss how this work is related to the current research landscape. We all know that machine learning is actively moving toward the edge right now. There are several pilot studies proposing ML on the sensor last year, including the work from Sammy et al. And our research group. Orthogonal to ML on the sensor, compressive sensing, fog-assisted sensor control, and next-generation energy-aware IoT networking are also promising research topics that can make wearable sensors much more suitable for continuous physiological monitoring. We are positioning this work as a theoretical extension of ML on the sensor, specifically addressing the computation energy trade-off.
While in principle many candidate neural networks could be used to realize the selective function, popular models suffer from excessive resource and memory usage that limit their deployment on resource-constrained MCUs. Consequently, we choose a one-layer fully connected network that enables efficient realization on the MCUs thanks to its smaller memory footprint and modest resource usage. The selector captures the sequence-to-sequence relation between the raw signals and the labeling. A current prediction depends only on the input samples in the batch. Neural networks are prone to overfitting. Numerous techniques have been proposed to prevent overfitting like wait decade or dropout that act on the hidden activations or waste of a neural network. Alternatively, regularizing the output distribution of neural networks have largely been unexplored. Confident predictions correspond to output distributions that have low entropy. A network is overconfident when it places on probability on a single class in the training set, which is often a symptom of overfitting. As you can see in the figure, a softmax distribution where probabilities are either 0 or 1. In order to save energy, it is important to minimize the number of selected samples. We handle the problem through output regularizations. This technique is inspired from a paper from Professor Hinton and his colleagues. To penalize the confident output distributions, we add a negative entropy to the negative log likelihood during training. The confidence penalty leads to a smoother output distributions, as can be seen in the figure, which results in a better generalization. Moreover, in order to make the network being more cautious in classifying a sample as abnormal, magnitude regularization is imposed on the output in combination with the added negative entropy to penalize confident output distributions of positive samples.
All of our experiments are conducted on a real-world platform we call EcoBP. EcoBP features a novel piezocapacitive sensor that can record continuous blood pressure non-invasively from a person's radial artery. The target microcontroller is an ARM M4 processor embedded in a popular Bluetooth SoC nRF52832. We are open sourcing the whole EcoBP platform, including the hardware, the firmware, and the Python application to the research community. Please feel free to reach out if you are seeking collaboration. This slide is an overview of the experimental setup. The setup includes a laboratory computer, an arbitrary waveform generator, analog discovery tool, and the EcoBP platform. To exercise the system in a controlled and repeatable manner, we implemented a radio pulse waveform synthesizer with hidden Markov model that generates synthetic continuous blood pressure in conjunction with the latent abnormality variable. The lab PC can then orchestrate each experiment run that involves synchronization of the arbitrary waveform generator and the device under test, the EcoBP board. To record real-time energy consumption, we integrated a battery field gauge on the board to sense current flowing into the Bluetooth SoC and the analog front end. Note that EcoBP are both connected to the supervising lab PC, both wirelessly and wired. The wireless channel is meant to transmit the selected samples, and the wired interface is responsible for communicating control signals and real-time power consumption. After each run, the lab computer can compute performance metrics based on the transmitted signal with the ground truths outputted by the synthesizer. We will define the evaluation metrics in the following slides. Matthews correlation coefficient, or MCC, is the primary performance metric we employ in evaluating the selector. MCC is chosen over other metrics such as accuracy and F1 measure because of its insensitivity to class imbalance and symmetry between true positives and true negatives. The symbols TP, TN, FP, and FN denote the number of 4 possible outcomes of a binary classifier. For example, if the abnormality event is as rare as 3%, a classifier that always returns normal will achieve an accuracy of 97%, while this unuseful classifier has MCC of 0, which reflects its deficiency. This is why we choose MCC as our primary metric. So the overall strategy will be maximizing the ratio between MCC and energy consumption, thereby achieving a system that matches our ultimate objective. We propose a figure of merit, which is the overall matrix, to evaluate the advantage of STINT. That measures the ratio of MCC and total energy consumption E in microjoules. To further analyze STINT, we've defined 2 additional quantities, namely recall and precision. Recall, or sensitivity, is defined as the count of transmitted abnormal samples to the raw count of abnormal samples. And the precision P is defined as the ratio between transmitted abnormal samples to the total number of transmitted samples. So higher recall is desirable in STINT because less abnormal samples are missed. On the other hand, high precision is also desired because less normal or unnecessary samples are transmitted. Both energy E and MCC will be determined empirically on the EcoBP platform. The top plot is the time domain example of a raw blood pressure waveform that is inputted to STINT. The bottom plot shows the ground truth labeling of abnormality along with the probability estimates reported by the MLP. You can see that most of the abnormal samples are transmitted precisely. The table summarizes the performance of STINT among different decision thresholds. The optimum figure of merit 102.3 occurs as threshold equals to 0.5 and the regularization coefficient lambda equals to 0.7, where the STINT-enabled system can achieve 14% of relative energy saving over the native system. Overall, the system has 27% gain in terms of the figure of merit. Besides, precision increases significantly from 0.23 at the baseline to 0.95 at the optimum setting, while recall drops from 1 to 89%. In terms of energy saving, this is desirable since the higher the precision is, the lower the total system energy will be. Nevertheless, depending on different medical contexts, we can choose a more relaxed setting of a lower tau and lambda to reduce the negative effect on the recall, so the abnormal portions of the raw signal can be completely transmitted. In this slide, we will be looking at 3 contour plots on energy consumption, Matthews correlation coefficient, and the figure of merit. The x-axis of each contour represents the strength of regularization, lambda. The y-axis is the decision threshold. For energy consumption, it is intuitive to see that it decreases as the threshold increases, because when the threshold is set to 1, only the samples that are known to be 100% certainty to the selector will be transmitted. On the other hand, the classifier performance in MCC reaches its maximum near threshold of 0.5. If I were to pick an optimum pair of design parameters, I would select a point along the highlighted yellow line because it yields the maximum MCC and is also closest to the point where energy consumption is minimized. Now if we focus on the contours of MCC and the figure of merit, we can immediately tell. If we focus on the contours of MCC and figure of merit, we can immediately recognize their similarity. Note that the boot-shaped isoplast also fits completely inside the isoplast in the energy consumption contour, sharing the same region of design parameters. The fact that energy consumption is roughly constant within any MCC level suggests optimizing the MCC is sufficient for maximal figure of merit. Here are the takeaway messages of this presentation. First, the STINT framework explores the frontier of ultra-low power wireless sensors by exploiting cheap MCU computation. The core technique of STINT is to leverage a compact deep neural network on the sensor as a proxy of task knowledge to select and transmit only the informative parts of the raw signal. A real-world continuous blood pressure monitoring application demonstrated that STINT can potentially save 14% of energy on healthcare IoT sensors along with minimum recall degradation. The authors would like to thank members from UCI Dutt Research Group and Kind Lab for discussion and support. Please feel free to reach out to me via my email taoyil@uci.edu if you have any questions. Thank you for listening to my presentation.